How did a team of engineers nicknamed the Extreme Team build a futuristic research station in the world's most extreme climate?
It's a really savage environment for any building to endure. It's just really harsh out there. You have temperatures that go as low as -58 degrees Celsius, and then you have wind speeds that go as high as 160 kilometers per hour.
How does this stunning visual trick make a 3.5-ton concrete arch levitate?
It looks like the wing is floating completely unsupported.
And how did they build the world's first rotating boat lift, able to carry 500 tons of water and 2 boats over 20 meters into the air?
All the Falkirk wheel needs is the equivalent power of 8 boiling kettles.
This is the age of the extraordinary.
This house always is on the verge of falling down.
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? Imagine the engineering it takes to build an advanced scientific research center that can cope with outside temperatures of -50 degrees centigrade and house 60 people. It has to be completely self-sufficient for months on end and be able to move locations quickly when danger strikes.
It's a brutal environment for any building to survive in.
But that's the building the British Antarctic Survey needed. A mobile research station that could survive in the most hostile place on Earth, Antarctica. This ingenious series of rugged pods uses train and space shuttle technology so that top scientists can study our planet's atmosphere all year round. But designing something that could be built on a slab of ice 10,000 miles from home was a massive challenge.
The people who were building it had to actually use electrically heated gloves to counteract the frostbite.
The crippling cold was only one of the hurdles a dedicated team had to overcome to pull this off. Every part had to be delivered to an ice dock that could crack open at any moment. Snowdrifts would bury buildings and equipment in the blink of an eye. And the summer build season was so short, it would take 5 years to complete. The result was the extreme mobile research station called Halley 6. So how did they build it? For the last 65 years, Britain has been pioneering the scientific study of the Earth's atmosphere in the most extreme environment on Earth.
This place has 1.2 meters of snow a year, and the snow that does fall, it never melts. Then you have the drifts. This is a big, wide, open space, so anything that you put there is going to gather a lot of snow on it.
Despite the tough conditions, the clean air and low light pollution are the reasons why the British Antarctic Survey has been building research stations in the Antarctic since 1956. In 1985, its scientists discovered a huge hole in the ozone layer, a finding that led to the global banning of CFCs, reversing a potential catastrophe. Named after the great astronomer Edmund Halley, the first 4 Halley bases were simple structures that worked for a while, but always ended up buried deep under the ice. In 1989, they upped their game, building the 5th base on adjustable stilts.
So Halley 5 was quite clever because it has these screw jacks, which meant the building could be jacked up every year by 1 meter or 1.5 meters to help it escape from the rising snow level.
So Halley 5 could move upwards to avoid the snow. But there was a bigger problem it couldn't escape. Every year, the ice shelf it's built on moves 400 meters closer to the sea.
The Halley 5's legs were fixed into the ice, and so they had to throw that design away because there was a risk that the ice could break off and the whole thing could just drift into the sea.
It was time for a new, better Halley research station. Architect Hugh Broughton rose to the challenge of designing a station that could overcome the difficulties of being built and operating in Antarctica. From the start, he faced an unusual set of limitations.
Everything that needs to be delivered to Halley, first of all, gets unloaded from a ship onto sea ice, and that the maximum weight of component could be no more than 9 tons. Then the other challenge is that this building needed to be relocatable between 15 to 20 kilometers, so quite a decent move.
Being able to move the station to avoid being stranded on an iceberg topped the already formidable design criteria. Some radical thinking was needed.
The first thing we decided is that we should come up with a modular solution. So break the requirements of the British Antarctic Survey's brief down into a series of interconnected buildings. And the reason we did that is that those buildings could be disconnected and moved more easily from one site to another.
The modular construction is really fitting for remote environments like this, much like the International Space Station, where you can put things together bit by bit without having to dig foundations or anything that you would traditionally see in a more reasonable environment.
The 8 pods, there's 2 sleeping pods, 2 science pods, 2 generator and plant pods, 1 command pod, and 1 double height living pod.
Along with a team of expert engineers, the architects created a blueprint for what would be the most complete extreme environment accommodation ever built. 8 individual pods would be linked through enclosed gangways, like train carriages, to create one integrated living and working organism. To cope with the constantly rising snow, huge hydraulically adjustable legs would allow it to be raised and lowered, and each leg would sit on a massive teflon-coated ski. If danger threatened, each module could be detached and moved to a new location where the station would be reconnected, avoiding a catastrophe. The modular plan solved many of the problems the extreme environment presented, but there was no getting away from the greatest single challenge facing its construction. The super short summer building season of just 12 weeks between December and February.
The construction season in the Antarctic is unbelievably short. Days in January and December, which might be -5, suddenly at the end of February, beginning of March, you're working at -25. And that's pretty hardcore if you're working outside. So then you've got to leave your site for the following 10 months until you can come back again.
While the construction crew could fly in on a Russian transport plane, all their tools and supplies had to be delivered by ship. The logistics here were tough enough, but it was that short 3-month window when external work was possible that meant a traditional approach to construction was impossible.
The only really sensible solution was to prefabricate everything in a warm country, in this case South Africa.
To maximize efficiency, the engineers test-built 2 complete modules near Cape Town. This meant they could perfect components and train the construction team before shipping all the parts 7,000 kilometers to Antarctica.
The buildings were built is in a kind of kit form, and that's because it's hard to move things when the ship arrives at the edge of the sea ice.
The on-site build began in 2007, with icebreaker ships straightening part of the ice shelf edge enough to dock along the side. Once in position, everything was unloaded at breakneck speed. The planning had been meticulous.
We wanted to be able to unload components, for the components to be as big as possible within that weight restriction of 9 tons, and for all the parts to be able to click together as quickly as possible. The biggest part that we made was the steel frame which forms the base of each of the modules, which is basically a whole series of tubes joined together in a three-dimensional form to maximise strength, making it easier to move from the ship to the building site.
For 7 days non-stop, Caterpillar tractors pulled 500 tons of cargo 12 kilometres inland to the still functioning Halley 5 base. The result was an extraordinary collection of prefabricated components awaiting assembly on the ice.
Everything was arranged in a very well organised, very well labelled line, 4 kilometres long.
The plan was to get each module on its legs and with all the key components fitted before winter arrived, shutting down the site until the following year. The construction crew of 40 men, who lived in prefabricated huts near Halley 5, worked in shifts around the clock to stay on schedule.
In order to maximise the efficiency of the construction process, we approached it in the same way almost that you would an assembly line for making a car or something like that. So we had one crew doing steel frames, another crew building shell.
Given the dangers of being in the Antarctic and the limitations on space, all of the builders had to be able to do more than one job.
There would be a team installing the primary building services, things like the generators, the sewage treatment, the water production unit, and then the service connections that go between the modules.
These are definitely no ordinary builders. In fact, they were nicknamed the Extreme Team.
Behind me is a second energy module with all the plant and equipment placed up on the floor deck. The obvious ones to point out are the big pink tank at the back, which is fuel, and the big grey tank at the front, which is water.
Every single unit that could be pre-built before arrival had been.
As you can see, there's the prefabricated bedrooms, plant room and WC. Next stage for this is to have the structural steelwork erected around it.
The bedrooms had the beds in, the desks in, the wardrobes. We didn't go as far as putting the duvets and the pillows on, but it was pretty close to that.
By the time the Extreme Team had the pod frames on their legs with the key components fixed inside, the days were becoming very cold and short. It was time to wrap the structures and prepare the site for the bitter winter to come. They could only hope the equipment and materials would survive.
So if you're going to leave any of your equipment there, you need to make sure that it's durable enough to withstand the harsh Antarctic winter. And that was a hard thing to do. There are materials which are used in food cold stores and things like that, but they typically go down to -25. But to say to someone, oh no, your product's actually going to go down to -55, that's sort of a different level.
In fact, it was discovered during testing off-site that the module cladding was too brittle. As a result, the following summer season, no work was done in the Antarctic, while the materials were perfected in South Africa. Finally, 21 months after wrapping them up, the Extreme Team returned and the half-built modules were released from winter's grip.
Okay, so here we are on the Halley 6 site. These structures are going to be towed up a ramp. The snow height here is about 20 foot at the back. So we'll clear it out, make a ramp, tow the structures out and take them to the south.
Cladding the modules was next. It was these improved panels that would give the Halley 6 pods their distinctive shape. A look inspired by a 50-year-old kids' TV series.
I can totally see this in the design, but apparently the architects and the engineers for this project were inspired by the 60s puppet show Thunderbirds.
I was a massive fan of the Thunderbirds. I think the influence is pretty clear. You know, Thunderbird 2 was coursing through the design from day one.
The Thunderbirds-inspired pods wouldn't just look good. Crucially, they would be the first line of defense against the harsh weather for everything and everyone inside.
The walls are made of glass-reinforced polymer, or GRP, and more commonly known as fiberglass. It's 75% lighter than the steel equivalent, and it's super strong, and it's lightweight, and it can actually resist corrosion. And best of all, it's a brilliant insulator.
Although fiberglass was known to be tough, Hugh needed to be sure it would survive the Antarctic conditions.
When we were having the glass fibre shell manufactured, we went through a really rigorous process of testing. We subjected it to the effects of the ice being blown in the wind, so we blasted it with sand to simulate that. We sprayed water at the cladding material or the building shell material, and then lowered the temperature really quickly to see what happens under freeze-thaw kind of cycles.
The glass fibre cladding, backed by 30 centimetres of high-performance insulation, would protect the researchers from the cold. But there is another extreme that people here need protection from, and that's the light, or lack of it.
We decided that at the heart of the station, in the main big red social module, it'd be really great if we could have a big double-height space with a big window, because you just get really nice light in the Antarctic in the summer, and it would just provide a really great social focus for the community. But of course, the big challenge you have in the Antarctic is if you create a big window, then it's also a source of massive heat loss, potentially. So we really searched high and wide around and discovered this incredible material that was invented by NASA called nanogel.
Nanogel was used on the Space Shuttle nose cone to protect it from the extreme heat of re-entry, but is equally effective at protecting from extreme cold. It also happens to be translucent.
Around 50% of light is actually transmitted through this material, so we have this big window at the heart of the station which allows lots of good natural light in without letting lots of heat out of the building.
With 400 meters of the ice shelf flowing out into the sea every year, by December 2011, the third season of the build, it was time to tow the modules 15 kilometers inland from Halley 5 and the ever-approaching edge. But by now, with modules fully built, even the smaller blue pods weighed as much as 100 tons.
The biggest challenge to getting the pods to their new home over the last 15 kilometres was overcoming something called stiction. This is the static friction that needs to be overcome to get objects to move.
The designers turned to a very common material found in almost every kitchen.
The skis are made out of high-grade steel that's suitable for a cold environment, and then they have a layer of Teflon, which is essentially fixed to the underside to help them to glide across the ice.
The skis were so effective, the extreme team had to make sure the 100-ton pods didn't run out of control.
H2, last night it was pulled off the construction line at this end, turned around, and a few tests done on it. What we're interested in is how slowly can we tow it, so how easily we can control it, and how quickly we can stop it, or what the stopping distances are. Because when you get to the other end, it will have to be a certain distance apart.
Being twice the size of the blue modules, moving the big red command module presented a much bigger challenge.
We're definitely over 200 tons with it, so just out of our comfort zone slightly. But good team on the job. If anybody can shift it, we can.
Moving the 8 modules the 15 kilometers took days. And as each module arrived to meet its new next-door neighbor, they were introduced with a bang. Fortunately, the connecting gangways were tried and tested super tough components.
They connected the pods using a double-layered version of the kind of concertina connections that you see in many railway carriages.
They're insulated when they're used in the Scandinavian countries. So again, it's normally used in the rail industry, but we just transferred it over to our buildings.
Finally, all 8 modules were linked and sealed from the weather. The only exterior connection, one safety gantry, an intentional fire break to protect one set of modules from the other in the event of a catastrophic fire or explosion. The last job of the year was to prepare Halley 6 for the next blast of winter.
Because the snow level is constantly rising, what you do is that each leg in turn, you lift it up using the hydraulics, You push snow underneath to make a platform of around 1 to 1.5 meters. And when you've done all of the legs, you then use the hydraulics again to jack the building up so it's sitting on these snow platforms well above the surrounding ice level. And then when it snows and the wind blows snow around over the winter and the level rises by 1.5 meters, it brings the whole thing kind of up to a level again.
In February 2012, over 5 years after the build began, Halley 6 came into service as the British Antarctic Survey's new research base. Its 60 occupants had never known such luxury.
If you're gonna do research and you're gonna live in one of the coldest places, if not the coldest place on Earth, then the least you can do is have a really cool place to chill in.
Halley 6 is without doubt the most complete extreme environment accommodation ever built. But in the Antarctic, Mother Nature takes no prisoners. In 2016, a huge new 150-meter deep crack appeared in the ice shelf. Just 30 kilometers from Halley and moving fast, it posed a grave risk to the station and the team.
This crack was discovered on the 31st of October 2016, so it's known as the Halloween crack, and it was moving at some speed. And so they then took the decision that because there was one crack going in one direction and another at 90 degrees, that the new site for Halley 6 had become far more dynamic than they had originally envisaged. And there was risk of leaving people over a winter, of not knowing how those two cracks would interact.
They decided to act. It was time to test out Halley 6's built-in mobility and move the base to safety and a new site inland. It was a timely reminder of how brilliant engineering and design can make the impossible possible.
Somebody living in an Antarctic research station, their life is at risk constantly because of the extreme environment. So you need to think of every single situation. Building a research station in the Antarctic is equivalent to building a Formula 1 racing car. You just can't leave anything to chance. There are a number of parameters that you have to design within, and you have to give each of them a great deal of respect, because failure to do so will be catastrophic.
(9,500 kilometers north of the Antarctic Circle, just off the coast of Morocco, are the Canary Islands. With year-round sunshine and warmth, buildings here have no need to protect their occupants from harsh weather. Instead, they can be built purely to celebrate their surroundings and purpose. Which is exactly what this incredible concert hall was built to do. Its 130-meter-long, 3,500-ton arch is engineered to hover above the auditoria below.
It's an incredible optical illusion. It looks like the wing is floating completely unsupported.
It's the improbable made to look impossible.
Inside is a stunning space for over 2,000 music lovers. But it's outside where the building hits the high notes. The incredible 58-meter-tall arch is only possible thanks to a secret skeleton of hardcore steel. The concrete cladding that creates its skin was so pioneering, an extraordinary new machine had to be custom-built to make it. Curved walls glisten with over 3 million tiny handmade tiles, and the giant wing flexes in the powerful wind. Auditorio de Tenerife is a stunning engineering performance. So how did they build it? In 1997, work began on a new concert hall in Santa Cruz de Tenerife in the Canary Islands. Spanish modernist architect Santiago Calatrava, who'd recently finished the awesome Oculus Transport Hub in New York's Trade Center, had designed a building that could match any music venue in the world for visual drama. Both inside and out. His design of flowing forms performing impossible engineering gymnastics, all clad in seamless concrete, would be one of the greatest construction challenges of its time. The most difficult to build would be the three curved components at the heart of the structure. Each would have a nickname. The nut would be the 45-meter-high central building to house the two performance auditoriums. It would also provide a single point of crucial support. The nut would be flanked by the two sails. These curving slabs are actually the outer walls of the main concert hall. On top is the wing. This massive structure, weighing the same as 10 747 aircraft, would be made of a steel frame clad in a thin layer of very ingeniously cast concrete. It would rest on that small point of support provided by the nut.
To create a structure like this, there is no off-the-shelf solution. You have to create something entirely from scratch.
The bespoke building technique that was key to the creation of Auditorio was the concrete formwork that created its cladding.
The simplest form would be to take two wooden boards, support them in place, put reinforced concrete in the gap in between, fill it all with concrete, let it set, and take the boards away and you've got a board.
Concrete formwork can be used like blocks to build walls. One layer added on top of another as many times as the steel reinforcing inside allows. Stacking layers like this is how engineers virtually hand-built the huge concrete walls of the sails. But the massive tapering, arcing wing would present a completely different challenge and a solution that was a world first. By 2001, the nut and sails were structurally complete. It was time to build the giant wing. Like the sails, the surface of the wing would be concrete formwork, but hidden inside would be the heavy-duty engineering that made this outrageous shape possible. A huge steel framework was prefabricated in Spain and shipped in 17 pieces before being assembled into larger sections on site. Juan Carlos was the site engineer.
Each piece weighed around 200 to 250 tons. They were lifted with a crane, and once they were up, a system put together the mobile and the fixed part, welded it, and then let it go. It's unique.
You have a steel skeleton that was constructed to give the whole thing a rigidity and strength. 24 rows of beams.
Once the steel frame of the wing was assembled, scaffolding was built under the inner areas to support traditional wooden formwork molds. But using formwork to make the concrete outer shell on the huge areas of the wing was not an option. Mainly because using the scaffolding required to work at such heights and difficult angles would have been impossibly slow, complex, and expensive. These problems meant the construction company had to come up with something special.
With the wing, the big curve, this was such a complex process of engineering that they had to design a special machine to put the iron and the concrete in, and this was supported by the same steel wing. It's unique and was built especially to do that.
This machine is called a carriage crane. It was assembled on the back of the wing, and its huge arms wrapped around and underneath to support the formwork. Adjustable in every direction and guided on huge rails, it enabled concrete to be attached along the wing in previously unreachable places.
This was a very slow process to create the wing. They had to align the formwork, pour the concrete, let the concrete set, then move the machine up and realign the formwork in a different, narrower shape and a different angle, and then re-pour the concrete and let it set and repeat that 32 times.
The final result is an extraordinarily fluid shape that, despite weighing 3,500 tons, appears to levitate.
This is an amazing optical illusion because when you look at it, it just looks like this wing is just completely floating in space. But from certain angles, you can see behind the smoke and mirrors.
The wing is supported at just 5 points. An amazing feat considering the powerful winds that almost constantly sweep across the Canary Islands. But one of these supports is a special steel shock-absorbing tube that moves up and down with the wing to stop it from tearing itself off the building.
In really high winds, you can hear it just bouncing up and down, which I'm sure sounds pretty terrifying, but I'm sure they knew what they were doing.
The Auditorio's architect, Calatrava, wasn't satisfied with just making the concrete achieve impossible shapes. He wanted his building to have an outstanding surface too. The concrete was mixed with a high proportion of sand and titanium dioxide to brighten it almost to white. But Calatrava wanted more. To make the building gleam, he wanted it covered in 3.5 million tiles, all hand-laid in a style called trencadis. But surely, even on this project, that was going too far.
Basically, trencadis means broken ceramic tiles on together on the same word, right? Anyway, mosaics is good. And I will show you they are 1 square meter panels that came pre-made on a flexible net from Valencia with different numbers. You can see like a wave, a zigzag cut, right? Can't you? And just 1 meter up, there's another one here, right? And there's another one over there. Once you have this information, you can see the different levels of this surface. We have made a jigsaw puzzle here.
Truly, the only word that comes to mind is spectacular. The effect you get when the music plays, something that truly transports you.
Close inspection may reveal a small cheat, but stand back and its full effect is plain to see. It all adds to create a glistening introduction to a music lover's evening. In Scotland, 20 years ago, an audacious plan was hatched to reconnect 2 of Britain's most historic canals. They were only 300 meters apart, but one was 24 meters higher than the other. For waterways that were once the superhighways of the Industrial Revolution, that is worlds apart. But an effort to reconnect these 2 canals overcame the huge problem with an engineering solution of stunning simplicity and efficiency.
This is the only Ferris wheel boat lift in the world.
This is the Falkirk wheel, a fusion of sculpture and engineering, breathing new life into a historic canal, and now a tourist destination in its own right. The wheel can effortlessly lift nearly 500 tons of water and 2 boats through 24 meters while not spilling a drop or breaking sweat. So how did they build it? 250 years ago, these narrow channels helped transport goods around the country, fueling Britain's booming economy. Here, the beautiful Union Canal runs to Glasgow in one direction, and the Forth and Clyde Canal runs to Edinburgh in the other.
These canals were the lifeblood connecting Edinburgh and Glasgow during the Industrial Revolution. And it also provided a luxury high-speed service, the bullet train of its day.
The waterways were completely reliant on a system of locks, which allowed these 2 canals at different heights to be connected. But by the late 1800s, trains were all the rage, and the canals and crucial lock system between them was barely used.
Due to the height difference between the Forth and Clyde and the Union Canals, 11 locks were needed to get the boats from one to the other. But these fell into disrepair in the 1930s.
Perhaps not surprising when you consider taking a boat through these 11 locks took almost an entire day. Eventually, they were demolished, and the stretch of locks and the waterway between them lay disused. Glasgow and Edinburgh were no longer connected by canal.
It was broken, fractured, you might say, during the 1960s and 70s with roads and other obstacles.
By the mid-1990s, canals were back in fashion, now used for pleasure rather than industry. British Waterways wanted the old route restored. To join the canals, they would have to dig a new canal, but overcoming a massive height difference was more tricky. Rebuilding the hopelessly slow staircase of locks that once connected the two canals at different heights was not an option. So in the mid-1990s, the search for a modern solution began. The design that was given the go-ahead was a completely original concept.
This is the world's first rotating boat lift that can take boats in a circular direction from one canal to the other. What we've created here is a piece of sculpture that becomes a landmark and a destination for Scotland.
The Falkirk wheel is a 200-ton steel Ferris wheel with two gondolas or caissons pivoting around a giant central axle. The caissons act as huge buckets that hold water and the boats. The wheel turns, moving the boats and 500 tons of water to connect them 24 meters above or below to the other canal. At the top, it's all connected by an aqueduct that would have done the Romans proud. And the Romans would prove to be this project's first obstacle. A Roman earth fortification once stood here. Today, all that's left is a grassy hill, but 2,000 years ago it was the most northern border of the Roman Empire.
Where we stand is the UNESCO World Heritage Site, which is the Antonine Wall, and that was built in AD 142. So we had to actually get the canal underneath the Antonine Wall through a tunnel. The tunnel was about 200 meters long, 8-meter diameter, onto the north side of the Antonine Wall, extend it onto an aqueduct, and then onto the Falkirk wheel.
Digging a 200-meter tunnel under the Antonine Wall was achieved without drama. Building an aqueduct 25 meters high over the basin was a more serious challenge.
If you had been here 20 years ago, what you would have seen is a whole forest of scaffolding. So everything was supported by scaffolding, so it basically takes a small part of the load of the wet concrete as you're pouring it. And as the 4 piers are poured, we get up to the deck itself. That's all supported and all constructed in 4 sections.
No one had built a canal in Scotland for 200 years. That lack of practice initially caused a few more problems.
Inevitably, there were some leaks. Not in the structure, I would have to say, but in actually the earthworks approaching to the viaduct. But over a series of a few weeks or month, we actually plugged all the gaps in the waterproofing of the canal, and then on a go. And to my knowledge, it's never had a problem in the 20 years since it's been open.
With the Forth and Clyde Canal connected through to the aqueduct, the wheel itself could be installed. This system required trapping 250 tons of water in each caisson and moving one up and the other down 24 meters to the basin below. To engineer a structure able to carry 500 tons of water on the end of 2 steel arms while keeping everything steady and under control meant relying on some key laws of physics.
It's like a balanced beam, and that weight really means it's very, very efficient. And the water and the boat balances out. So we had the unique balanced beam idea that I don't think there's another boat lift that uses that principle. It uses other elevator type principles with weights and things, but not a balanced beam, which is the fundamental system here.
The natural balance of having equal amounts of water at each end makes sense if both the caissons have a boat in. But how does the Falkirk wheel stay balanced if it's only transporting one boat and the other is empty? To answer the question, engineers made clever use of the Archimedes principle.
Archimedes had a eureka moment when he realized that if he put an object in his bath, the weight of the object was displaced exactly with the water. And it's the same principle here.
So in this case, as a boat floats into the chamber, it's going to remove the exact amount of water that's equal to the weight of the boat. So that means that as long as you keep the water levels the same, it's going to continue to weigh the same, with or without the boat.
Now, the massive payload needs to be rotated.
Normally, moving 500 tons of water 24 metres in the air takes the same amount of energy as a typical Scottish household over 3 days. But all the Falkirk wheel needs is the equivalent power of 8 boiling kettles.
The balancing act means the wheel is easy to turn. As the wheel lifts one tank, the downward force of the tank on the other side does most of the work. Like a seesaw, water keeps the wheel balanced, but it creates another problem. Each massive tank contains 250,000 litres, and if this water starts sloshing from side to side, there could be trouble.
The biggest problem is the water. You have to keep the gondolas or the tanks level. Plus, when you start to move water, it creates a critical mass that's really hard to stop. The entire structure could tip over if it's not carefully controlled.
We had to solve the problem of how to stop the water from making the caissons turn over. Because as you move them around, they're inherently unstable. You know, if you take a ferry full of water and the water flows from one side to the other, you know, it's very difficult to control it once it starts to move.
The best solution proved to be the simplest.
It's connected by a simple system of cogs and wheels. We have 5 cogs, of which the central one's fixed, and the outer 2 are fixed to the caissons, and then the 2 wheels in between are allowed to freely move around. And what they do is they allow caissons to always remain horizontal no matter what forces are applied to the 2 beams going around.
As the wheel turns, the central axle drives cogs that run up the arms of the wheel. These are geared to create an always correct connection to the caissons, which stops any internal forces affecting their position, prevents the caissons swinging out of control, and keeps them permanently level and safe. The Falkirk wheel is the perfect marriage of beautiful design realized by clever engineering, reconnecting an historic canal route with a uniquely modern solution.
The finished wheel is a piece of pure engineering meets Celtic sculpture, providing a breathtaking example of how human problem solving can achieve the spectacular.
It's still very well attended. It's one of the main tourist attractions in Scotland, and it actually sits as an iconic structure within all the other iconic structures that have been built in the UK and in Scotland. And again, very proud to have been part of the team that actually delivered this.
It's in the British passport. You know, it's on the Scottish pound note. And it's really great that something of today that takes old technology and reuses it in a different way and is innovative in the way it approaches things is actually celebrated. And that, I think that's the best thing of all. You know, if people can enjoy and know that there's a future and there are more things to be discovered, that's the most exciting thing.